good afternoon, everyone. I am Soumyaranjan Ratha, PhD scholar of Akita University under the guidance of Professor Satoru Yoshimura. I am going to talk about the enhancement of magnetic properties by lanthanide substitution in bismuth ferrite multiferroic thin films. Before going to the work, I would like to explain about the importance of magnetic material in the case of magnetic memory devices. For example, in the case of hard disk drive, we write data on the platter by using inductive current by the coil. And in the case of STT-RAM also, we write data by using spin current. And in the case of newly discovered restrict memory also, we write data by using the spin current. So if we talk about the magnetic optical devices, for example, spatial optical modulator, which is governed by the process hologram method. And one most important thing I would like to note here, this device need high Kerr effect. So this also need spin current to write some data. In all the cases, we found one thing: to write data among any things, we have to either use spin current or inductive current, which really consumes high amount of energy and which is a problem. Let's discuss details about the problem in restrict memory for the energy consumption. As we know very well, this restrict memory is introduced by IBM in 2007, and there we'll find billions of nanowires to save data by the spin current. So to write data, if we use the inductive coil, we have to give current for the induction, and we have to provide current for the billions of coil. You can imagine how much energy it will consume. So it will consume high amount of energy. So instead of that, if we can use some material which will consume very less amount of energy and which can provide us the magnetic reversal, then we can remove these coils. So what can be the candidate material? Let's discuss about the multiferroic thin film. As we know, these materials show magnetic property as well as electric property. We can use this material. Let's see details how we can use. In the writing process, the polarization direction will be controlled by electric field. And in the second case, the magnetization direction of the metallic ferroelectric ferromagnetic layer will be controlled by magnetization. That means we don't need to apply spin current to change the magnetization direction. Simply by changing the polarization direction, we can change the magnetization direction. That means we can completely remove these coils, and instead of that, we can use this multiferroic material, and we have already patent on this application. But one most important thing I would like to say here, for any type of magnetic devices, two important features should have a material. The most important thing is that it should have perpendicular anisotropy and high saturation magnetization. Let's see. So among many material, as I discussed about multiferroic material, because it shows ferroelectric property and ferromagnetic property in the same page, and we know very well this shows perovskite structure, which is ABO3 type. That means it has A side and B side. If we'll see the schematic diagram, you can see the pink part represents the multiferroic material, and these are the electrodes. Means by changing the direction of the polarization, we are able to change the magnetization direction, which we really require. That means it consumes very less amount of energy, that causes very low electric consumption, and the fabrication is really simple, that causes low cost, and we are not using a noble material. That's really important, and that also causes low cost. So among many multiferroic material, I told I will consider bismuth ferrite. As we know, this has perovskite structure. The center is occupied by iron, the face is occupied by oxygen, and the corner is occupied by the bismuth. Other features are like it has spontaneous polarization along diagonal, and Curie temperature around 100 degrees Celsius and nil temperature around 600 degrees Celsius, which says that we can use this material in room temperature. So now we don't need to worry about the temperature. But there is a problem related with this material. It shows antiferromagnetic property, which is really a problem. So if we can solve this problem, we can use this material in our devices. Then we came across some papers. They are substituting few elements to enhance the magnetic property. In this paper, you can see they substituted barium in A side, and they enhanced the magnetic property and as well as electric property. And you can see the hysteresis loops are the signatures of the enhancement in magnetic property and electric property. That means we found one thing here: upon substituting few elements in the A side as well as B side, we are able to enhance the magnetic property. So we started fabricating devices by using pulse DC reactive sputtering with very high frequency plasma irradiation. Like all sputtering machine, we have a target and substrate. We use the plasma of argon and oxygen. This high energetic plasma hits the target and it detaches an atom and it moves toward the substrate and make thin film. The most important thing is that it has pulse DC. As we know very well, the plasma gradually accumulated on the target and it hinders the movement of extra plasma or more plasma to come toward the target, which really stop the process. So we have to remove this arc current, and that can be removed by using the pulse DC. And second most important thing is that there is no bombardment between the sputtered atom. One set of atom will come, this will be settled down by searching its potential region. Then another set of atom will come for the sputtering process. That causes high enhancement in the crystallization. You can find it, the result in the next slide. You can see this is the work already done by my group. They substituted barium in the bismuth ferrite, in the A side of bismuth ferrite. You can see this data shows RF sputtered bismuth ferrite, and this data shows pulse DC sputtered bismuth ferrite. This clearly shows that the magnetic property is 1.5 times larger in case of pulse DC than RF. That means you can understand how crystallization is matter in the case of pulse DC, and these are the hysteresis loops of magnetization and electric polarization or ferroelectric property. But there is a problem in this material. It shows in plane magnetic anisotropy. As I told, we need perpendicular magnetic anisotropy. In the second case, we substituted lanthanum in A side and cobalt in B side. You can see in this figure, first we substituted manganese, then the property was not so good. We substituted only lanthanum, little bit enhanced, not that much. But when we substituted lanthanum along with the cobalt in B side, it enhanced highly. That means, and the most important thing is that we got perpendicular anisotropy, which we were searching, that is perpendicular anisotropy in multiferroic material. That means the cobalt as well as lanthanum substitution is highly enhanced to and highly important to enhance the magnetic property. So now I'm going to study about the same material, but in different way. How can I enhance more the saturation magnetization, perpendicular anisotropy, and core angle? As I told, we are substituting few elements in A side and cobalt in B side. Cobalt is fixed. The first important thing we got after substituting cobalt, that means first I will study what is the optimized cobalt concentration at which I will get maximum enhanced magnetic property. After getting the optimized cobalt concentration, I will change different lanthanides by selecting few elements from rare earth element like lanthanum, neodymium, samarium, gadolinium, and dysprosium, and I will compare along all the materials which are really best for the device application. Let's start the investigation. So you can see, as I told, first I will see the cobalt dependence, keeping A side as lanthanum. Now I'll start increasing cobalt concentration in B side. So you can see with increasing cobalt concentration, my magnetic property or the hysteresis loop is getting enhanced, and something around concentration of 28, or we are finding it around 25. In the case of magnet optical effect, as I told, for the optical devices, core effect is really essential. So you can see with increasing cobalt concentration, core effects also getting enhanced. That means the cobalt concentration or the optimized cobalt concentration should be around 25%. So I completed the B side substituent, that is cobalt, and what percentage? That is 25%. Now I'll go to the A side substitution. Before that, we are trying to find the physics behind it. We are assuming when we substituted lanthanum, of course there is some interaction. We are thinking the magnetic moment is cancelled completely, for which it was showing previously antiferro. That's why the saturation magnetization was very low. But when we substituted cobalt along with lanthanum, the entire magnetic moment is not cancelled, rather few amount is cancelled. So we are getting ferrimagnetic. So here we also came across one paper by Professor Hiroshi Naganuma. They tried different B side substituent. Also, they substituted only cobalt. We didn't try only cobalt. They got it in plane magnetic anisotropy, but we got perpendicular anisotropy after substituting lanthanum. That means for our desired property, we need to substitute lanthanum as well as cobalt. So what's the physics behind it? That study we are going to do by the synchrotron radiation in recent future. Then I told I will substitute A-site elements with different rare earth element. You can see this is the neodymium substituted bismuth ferrite. It is really giving high enhanced magnetic property. At the last slide, I will compare how this is high among all the materials, and we demand this can be used for the memory device application. So now I told I will substitute few elements of rare earth element in the S side. So this is for lanthanum, neodymium, samarium. This is for gadolinium and dysprosium. You can see among all 5 substituents, the neodymium substituted bismuth ferrite is really showing high saturation magnetization. That means, of course, all these are showing perpendicular anisotropy. So this is the candidate material for our magnetic device application. In the second case, for the Kerr angle, you can see the lanthanum substituted bismuth ferrite is showing high Kerr angle. That means this material can be used for the optical devices. So if we again think about the physics, of course, we are doing something experimental, but we have to give the answer why this is happening. What's the physics behind it? So you can see when we substituted a barium, the enhancement is not so remarkable. But when we substituted lanthanum, this is enhancing so nicely. That means we can say the cobalt only is not important. Cobalt along with A-site lanthanoids is really important to enhance the magnetic property. This discussion is almost equal to the previous discussion that we are going to get by the synchrotron radiation. Maybe next year we'll do it. So this is the summary of my work. In the summary, I compared the magnetic property found by different substituents. Along all substituents, you can find the neodymium substituted bismuth ferrite is showing high saturation magnetization and very good coercivity or perpendicular anisotropy. That means this material can be used for the memory device application. Now think about the optical devices, that is Kerr effect. So among all, this lanthanum substitution is giving high Kerr angle. I already told the cobalt concentration is around 25%. So this material is better for the optical devices. So in the recent future, we are going to try other materials and other elements in the B side. And most important, what is the physics behind it? Why this interaction is happening and it's increasing. So this is all about my work. Thank you so much for your attention.
Thank you very much for that excellent talk. One quick question. Why is PMA important, and what if we have spin moments in the plane?
Okay, so now our intention is to get high areal density. Previously, we used in the magnetic devices in plane anisotropy, for which it causes the areal density very low. But after that, maybe from 2005, I'm not sure about the date, we are using the perpendicular anisotropy to find the high areal density.
Thank you very much.